Section 7-3, Estimating a Population Mean. In this section, we're going to take a look at sample means and finding estimates using confidence intervals. The first idea is to establish that x bar, the mean for the sample, is the best point estimate for mu, the mean for the population. We will construct confidence intervals and use this as an estimate for the population mean. We'll also take a look at finding a good sample size to determine the population mean. The basic requirements needed for this is to make sure that our population is normally distributed, or we have a sufficiently large enough sample size, usually 30 or greater. We will use a new distribution called the student t distribution. This distribution is defined by t is equal to x bar minus mu divided by s over square root of n. Now if you look at this formula and say this is kind of similar to our z-score distribution, that's because it is. The student t distribution uses the sample standard deviation instead of sigma, the population standard deviation. It also uses this idea of a degree of freedom. By definition, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all the data values. We usually use df for the degrees of freedom. For this section, the degrees of freedom will be n minus 1. That's the sample size minus 1. Some basic properties of the student t distribution is that we have a different distribution for different values of n, and because it depends on the degrees of freedom, and the degrees of freedom is n minus 1, we will have different distributions. The student t distribution is symmetric, just like the standard normal distribution. It has a mean of 0, and the standard deviation is a little bit different. Another important property is that as the n, or the degrees of freedom, gets larger, the student t distribution begins to approach the normal distribution. Here are some examples of the student t distribution. The blue graph is the standard normal distribution, our z distribution, and we can see a few t distributions with n is equal to 12 and n is equal to 3. We use a t distribution in our formula for the margin of error. Our margin of error will be defined by t sub alpha over 2. That's our critical value from the t distribution. And then we have s over the square root of n. One of the ways to get the values for the t distribution is through the table A3. But we'll see another way using a calculator. The notation involved here is that mu is a population mean, x bar is a sample mean, s is a sample standard deviation, n is the sample size, e is a margin of error, and t sub alpha over 2 is a critical value. Notice we don't have sigma here, and that's the whole reason for using the student t distribution, is because sigma is unknown. Let's take a look at an example where we're looking for 95% confidence and our sample size is 22. The basic idea for a critical value is to look for this value over here where alpha of 0.05 gets split up into two tails, and that's 0.025. So we can think about this as 2 tail alpha equal 0.05 or a 1 tail of 0.025. With our degrees of freedom equal to 21, we can look at the table. We can look at a 1 tail of 0.025 or 2 tails of 0.05 and a degrees of freedom of 21. And then we'll see that our critical value is 2.080. Another way to approach this is to use a calculator. Our calculators have a built-in function called inverse t, much like the inverse norm, except our inverse t uses an area to the left, and then it requires a degrees of freedom. To get this in our calculator, we press second and vars, and then we look for the inverse t, and then as an example, we would put in 0.05 divided by 2. So alpha is 0.05, we divide that by 2, and then we got 0.025. Now notice that this is the area to the left, and so this calculation gives us a negative 2.0796. So using symmetry, we'll just take a look at the positive side of that, and then we round out to 3 decimal places, and we get the same value as we got in the table, which is 2.080. So back to our confidence interval. We construct our confidence interval by adding and subtracting the margin of error to our sample mean x bar. So the procedure for constructing a confidence interval, if you were to do this by hand using the table, you would verify that the requirements are all satisfied, and then you would find your degrees of freedom and then use table A3 to search for your critical t value. And then you evaluate your margin of error, you add, subtract from the sample mean, and then you construct your interval, and then you round off. A quicker way to do this is to use the calculator. Using the t-interval, what we would do is we would press stat, and a couple of arrows to the right will give us tests, and then you scroll down and look for it. It's not going to be in the initial screen, but if you go down farther, you'll see t-interval. In the t-interval, we'll be looking for x bar, s, that's your standard deviation for your sample, your n, that's your sample size, and then your confidence level. Let's do an example. It says here that a common claim for garlic is that garlic lowers the cholesterol level. So we tested the effectiveness of garlic with 49 subjects. They were treated doses of raw garlic, and their cholesterol levels were measured before and after the treatment. So we want to look for the changes in their LDL cholesterol levels. And we found that for this sample of 49 people, we have a mean of 0.4 and a standard deviation of 21. So 21 seems like it's a large standard deviation, but let's take a look at how that plays out. We're going to use sample statistics of n is equal to 49, x bar is equal to 0.4, and the standard deviation s is equal to 21. And we want to construct a 95% confidence interval or confidence level to estimate the net change in the cholesterol. And then they ask us a follow-up, what does the confidence interval suggest about the effectiveness of garlic? First, let's make sure that the requirements are satisfied. We don't know if this comes from a normally distributed population, but our sample size is large enough, so I think we're good to go. So doing this by hand, you would find your degrees of freedom to be 48. If you look in the table, 48 is not on the table, so you look for the closest number, which is 50. There's 2 tails at 0.05, and you get 2.009. And then you use that to construct your margin of error, which is 6.027, and then you add and subtract that to 0.4, your sample mean, and then you get negative 5.6 to positive 6.4. So quicker than this, you can use a t-interval. When you call on t-interval and put in the values for x bar, 0.4, your Sx, your standard deviation is 21, your sample size n is 49, and the confidence level is 0.95, 95%. When you hit calculate, you will get the same result, negative 5.632 and 6.4319. So the only thing I'd prefer is that you write your confidence interval with the appropriate population parameter. So we see that the t-interval gets us our results a lot quicker. So let's finish this up. We can say in words that we are 95% confident that the limits of negative 5.6 and 6.4 actually do contain the value of mu, the mean of the changes in LDL cholesterol for the population. Because the confidence interval limits contain the value of 0, and the value of 0 is the idea that there is no change, it is very possible that the mean of the changes in LDL cholesterol level is equal to 0. So this suggests that the garlic treatment really does not have an effect in cholesterol levels. So we can state that also in words. It doesn't appear that the garlic treatment is effective in lowering the LDL levels. We might be interested in finding the margin of error. If you remember with the calculator calculations, they gave us the actual interval itself. And so if you're given the interval and you want to find the margin of error, we have a formula for that. That's the upper confidence limit minus the lower confidence limit divided by 2. You can also find your x bar from your confidence interval as well, just by finding the average. Let's shift gears now where we're looking for n, the sample size, to estimate the population mean. And so we'll be using the idea of the population mean, the population standard deviation, that's mu and sigma, of the sample mean and the margin of error. And then we're also going to be using, we're going to go back to the standard normal distribution, the z-score, z sub alpha over 2. The formula that we'll use is n is equal to the z sub alpha over 2 times sigma divided by the margin of error, all quantities squared. So let's take a look at this formula for a minute. In most cases, you'll probably be given some sort of confidence level that you want to be confident in your study, and then we're going to be given our desired margin of error. So sometimes the tricky part is to figure out if your sigma is given, and if it's not given, what value are we going to use for this sigma. Let's remember the round-off rule whenever we're looking for sample sizes. If you're looking for a sample size, we always want to round up to the next larger whole number. Since we're looking at sample sizes, the results must be a whole number. So back to the idea of finding out sigma. If we don't know what sigma is, and chances are we don't, we can use the range rule of thumb to find the range of values. We can estimate the range of values and then divide that by 4, and so that can be our sigma. You can also start a sample collection process without knowing sigma and then calculate your sample standard deviation for that. Or you can rely on a study that was done earlier of a value for the standard deviation. Here's an example. Suppose we want to estimate the mean IQ score for a population of stats students. How many students should we select if we want to be 95% confident that the sample mean will be within 3 IQ points? So let's try to extract all the pieces of information that we need. We have a 95% confidence, which tells us that our alpha should be 0.05. Alpha over 2 is 0.025, and you can punch that in your calculator for an inverse norm to get our critical value of 1.96. We need a margin of error of 3, and here our standard deviation is 15. Now, where did they get 15? It turns out that this was a study that was done earlier where the standard deviation for the IQ scores is 15. Now, that's not stated here, but it should have been stated here, I think. Otherwise, most of our examples with IQ scores have a population standard deviation of 15. So we punch that into our formula. We get z sub alpha over 2 times sigma divided by E. That was our formula, and that whole thing squared, and we get 96.04. Now, 96.04 is closer to 96, but remember that we always want to round up. So our final answer here is 97. So we can say that with a simple random sample of 97 statistics students, we should be 95% confident that our sample mean, whatever it is we get, will be within 3 IQ points of the true population mean. Now let's dive into another part of this section where we take a look at estimating a population mean, but this time we actually know sigma. Now, just a disclaimer, usually when you're trying to find a population mean, you don't know what the population standard deviation is. But there are going to be some cases in your problems that you're working on where you're going to assume some value for the population standard deviation. When we do that, we will go back to using z sub alpha over 2. We're going to go back to using the standard normal distribution. So we have a mu x bar, we have sigma n, and the margin of error E, and then our critical value. So the idea here is that we're going to examine when the sample is simple and random, and the value for the population is known, and then either or both of the conditions satisfied with the population is normally distributed, or n is bigger than 30. To find the confidence intervals, we'll use our margin of error of z sub alpha over 2 times sigma over n. So notice the slight difference between this and when using the student t distribution. Here sigma is known, and when sigma is known, we're going to go back and use the z score, the z sub alpha over 2, or the z critical point. And then the setup for the interval is generally the same. Now the calculator also has a command for this, and this is the z interval. Again, it's different from our t interval. And the z interval is usually in the bottom of the first page of your stat test page. So you hit stat, a couple arrows to the right to test, and then you'll see it in the bottom of the page, z interval. And you'll be inputting the same ideas where the sigma is known, x bar is used, and our sample size and our confidence level. So here's an example. People have died in the boat and aircraft accidents because of obsolete estimates of the mean weight of men was used. So in recent decades, the mean weight of men has increased considerably, so we need to update our estimate of that mean so that boats and aircrafts and elevators, etc., will not become dangerously overloaded. So we'll use the mean weight for men in a random sample and obtain that the sample statistics is n is equal to 40, and we have 40 people that we tested, and the mean weight is 172.55 pounds. So other research sources have suggested that the population standard deviation is 26. So here, in our example, we're going to use an assumed population standard deviation of 26. Notice S was not given, and if it was, we won't use it because of the idea that we know some information about the population standard deviation. So here's what we want. We want to find the best point estimate for the mean weight of the population for all men. We're going to construct a 95% confidence interval, and then we're going to try to say something about it. So the old mean weight that was used is 166.3 pounds, and so we'll make some conclusion based on what we find. So here's the first couple of steps. The sample mean of 172.55 will be our best point estimate, and then in finding the confidence interval, we will use our critical value of 1.96 and plug that into the equation or the formula. We get 8.057, and then we're going to add and subtract that to the sample mean 172.55. We're going to get our confidence interval to be 164.49 to 180.61. Using a calculator, however, we'll find that a little quicker. We will do the z interval. We will put in our sigma, that's 26. Our x bar is 172.55 with our n is equal to 40, and our confidence level of 0.95 or 95%. And you'll see that the result, 164.49 and 180.61, is exactly what we got using the formula. So based on our results, is it possible? It is possible that the mean weight of 166.3 used in 1960 could also be the mean weight for today. It did have this number within our confidence interval. However, the best point estimate of 172.55 would probably be a better point estimate to use. So considering an underestimate of the mean weight of men can result in lives lost through overloaded boats and aircrafts. So we probably should shift that idea to 172.55. Alright, so in this one section we've actually gone through a couple of different formulas or calculator commands. Essentially, we looked at two different distributions. We looked at the t distribution, and then we went back to the z distribution. So it's kind of important to figure out where to go from here and how to find which distribution to use. So there is an interesting flowchart to use. First thing we ask is that if sigma is known, do we know what sigma is? And if we do, we're going to follow this path. Is the population normally distributed? If it is, then we use a z distribution. We can also ask, if it's not normally distributed, do we have a sample size that's large enough? And if so, we'll go back to the z distribution. So if the population is not normally distributed, and the population is, or the sample is not large enough, then we can't use a z distribution, and so we're not going to cover that in this class. There's some other techniques of using non-parametric or bootstrapping methods that we're not going to cover. Alright, so if sigma is not known, then we have to rely on this thing being normally distributed. We hope that this comes from a population that's normally distributed, and if so, then we get to use a t distribution. If it's not, then we have one more chance of having a sample size that's large enough, and again, if the sample size is large enough, then we use a t-distribution, and then we're all good. If it doesn't satisfy any of those, then we go back to this idea of non-parametric or bootstrapping methods that, again, is not covered in this class. Okay? So here's another summary. We use a normal distribution if sigma is known. We use a t-distribution if sigma is not known. Okay? So that's the general idea behind our problems for this section. That's the end of section 7-3. Good luck.